Let's take a look at what happens if my solution concentrations are not 1 molar. Remember, when I have 1 molar concentrations, I'm dealing with standard conditions. So if I take a look at this reaction where I have copper metal with 2 cerium ions going to copper ions, and cerium ion has reduced its charge, I can measure an E0, or actually calculate an E0 of the cell of 1.36. But what happens if my cerium concentration is greater than 1 molar? Well, if my concentration for cerium ion is greater than 1 molar, what that means is that's going to push my reaction to the right if I think about the equilibrium stuff. And so the reaction favors the forward direction, so my E0 of the cell should increase and should be bigger than 1.36 volts. So let's see if we can figure out what's really going on here and why that happens. We're going to start out very simply by looking at a silver cell where we have silver ions in both sides and both of our electrodes are silver. So on the left we have a 1 molar solution of silver ions and a silver electrode. On the other side we have a 0.1 molar solution of silver ions, and silver is our electrode. And we've got to figure out which way they're going. If both cells were 1 molar, then no electrons would be moving, so my E would be 0. Since the concentrations are not equal, I actually get an electron flow. So let's see if we can figure out which way the electrons are going to flow and why it's going to work. So in both cases, I have silver ion plus an electron going to silver metal. The E0 for this cell, or for this half reaction, is 0.8 volts. What equilibrium wants to do is to make the concentrations equal. If that's the case, what that means is the concentration on the left is going to have to decrease in silver ions. The concentration on the right is going to have to increase on silver ions. So on the left side, I have silver ions reducing to silver metal. And on the right side, I have silver metal giving up an electron to form silver ions, so the concentration will increase. So if on this side the concentration is increasing, that means that my electrons are leaving this side. They're traveling across the wire. They're coming in here so that the silver ions can be attracted to the electrode and form silver metal. Now it turns out the potential, the electrical potential for this cell is really small, but it can be measured. And the way I calculate it is using an equation called the Nernst equation. From our last chapter, we saw that delta G at non-standard conditions equals delta G0 plus RT ln Q. Q, remember, is my reaction quotient because I'm no longer at equilibrium. And we've learned just now that delta G0 equals negative NFE. So now I'm going to put these two together. So if I substitute in delta G0 with negative NFE, what I get is this equation here. E equals E0 minus RT NF times the natural log of Q. Remember, N equals the number of electrons. And at 25 degrees Celsius, the constants of R and T and F times the natural log of Q are equal to 0.0592 times the log. So this is an equivalent that you may find useful. Sometimes I think they switch from log to natural log just to keep you on your toes, because we've dealt with natural logs up until this point, and then all of a sudden now for electrochemistry we're switching over to logs. At any rate, you can handle it. So here's my equation. I've taken R and T because we're at standard conditions for temperature. So temperature is a constant, R is a constant, F is Faraday's, that's a constant. So these three I'm putting together, and what I get is the Nernst equation, which is this equation right here. And that's what I'm going to use when I have to deal with electrochemical cells where I am not standard concentrations. And this will help me figure out which way the equilibrium is going to shift because I'm dealing with Q and not K. So going back to our silver reaction, on the left side I had silver ions, the 1 molar solution. On the right side I had the silver ions, the 0.1 molar solution. So there's my reaction. So Q is going to be concentration of products over concentration of reactants. Remember, this is a silver electrode on the left, it's a solid. This is a silver electrode on the right, it's a solid, so they don't get put into equilibrium expressions. So I have 0.1 over 1, that's easy, it's 0.1. So my equation is going to look like this. E0 for the cell is going to be 0.8 volts minus 0.8 volts, so the E0 for the cell is going to be 0. So I put all of this now into the Nernst equation. So here's my E0, N equals 1 because I have 1 electron being transferred from silver ions to silver metal. I'm taking the log of 0.1 because that's my Q, and so the electrical potential for this silver cell is 0.0592 volts. Again, like I said, it's a very small quantity, but it is measurable and it's definitely calculatable. Okay, if we go back to the reaction we started with, where we have copper plus cerium 4 ions going to copper 2 and cerium plus 3 ions, we have a cell E0 for the cell of 1.36 volts. Now what happens when we change our cerium ion concentration from 1 molar to 0.85 molar? Well, we have a copper concentration of 0.75 molar, and we have a cerium plus 3 ion concentration of 0.15 molar. Now what do we find we have for the E0 for the cell? First thing we need to do is figure out Q. Well, products over reactants. I have 2 ions as products, so the concentration of copper ions times the concentration of cerium ions, and I have to square it. Remember how to do equilibrium problems. And then on the reactant side, I have the concentration of cerium plus 4 ions, so that's going to be 0.85 molar. And if I look at my reaction, I've got a coefficient of 2, so I've got to square that. Solving for Q, I get 2.34 times 10 to the negative 3. So now if I'm looking for E, remember that's E0 minus 0.0592 over N times the log of Q. E0, we saw up at the beginning, is 1.36 minus 0.0592. N, what's N? How many electrons are transferred from one side to the other? Well, if I take a look at the reaction, if I figure it out, what I'll see is 2 electrons are transferred, so N equals 2. Then I have the log of Q, which is 2.34 times 10 to the negative 3. So what I find is I get a cell potential of 1.44 volts. So because my concentrations of cerium ions on the product side are way less than 1 molar, even though my concentration of cerium plus 4 on the left is less than 1 molar, I still have that driving force making me go towards the product side. My concentration, again, of copper ions is less than 1 molar. So copper is going to want to oxidize to increase that concentration. So both of those facts combine to increase the driving force of my reaction. So I have a higher cell potential than I would have at standard conditions. So as the driving force of the reaction decreases, in this case it increases, so does the E0 for the cell. When I have Q equal to K, then I have delta G0. Again, we learned that from our last unit because I'm at equilibrium. So at equilibrium, delta G is 0. And at equilibrium, E is 0. So when I have an equilibrium situation in my electrochemical galvanic cell, what I have is a dead battery. Some batteries tend to be multiple electrochemical cells linked together in series. And so I have the sum of each of my cells. And when I add them all together, that's what's going to give me the total voltage of a battery. So again, a battery is, in some cases, multiple electrochemical cells, and they're connected in series. What we'll look at next is a variety of different kinds of batteries, how they are created, what chemicals are involved, and what makes some batteries reversible.